Okay, we're going to jump straight into 10.7 now. So now we're going to be looking at power series. Everything we've been doing in this section of this chapter so far has been leading up to these last few sections. We've looked a lot at series that just had constant values that we were adding to infinity, but now we're going to be looking at adding polynomial functions to infinity. So a couple of quick definitions and theorems here. So just the definition of a power series. A power series about x equals 0 is a series of the form, and then it looks like this. So if we have our infinite sum as n goes from 0 to infinity, we're going to have some constant values, and these are just any coefficients out in front, and then we're going to have these powers x to the n. So if we were to write out a few of these terms, I would just have a constant term out in front, plus a constant times x to the 1, plus a constant x squared, plus a constant x cubed, and then this will just keep going forever and ever and ever. So it's this infinite polynomial with coefficients, and then my power functions x to the power n. This is a definition of a power series that it's centered at 0. What it means to be centered at 0 is that this gives us values where x is close to 0, and it kind of messes up as x gets further away from 0. You can move this over slightly and look at power series about the constant x equals a instead. So all we do here is the same general idea. We're going to have our infinite series, n goes from 0 to infinity. Still have our constants out in front, but now we're just shifting our function to the right by a, or to the left if it's a negative a, to have this new power series. So with this power series, we've got a that we have here. It's called the center. And of course, we have our coefficients, being c to the n. So just a quick example of a power series here. Let's look at the most basic power series that we can do. This will be the series n goes from 0 to infinity of just x to the n with 1s as coefficients out in front. So to write out a few of these terms, 1 plus x squared plus x cubed, forever and ever and ever. Okay. If you think about what is going on with this series, this is going to be a series that starts with a coefficient of 1, and then every time we get to the next term, we are multiplying by a value of x. So this is really just a geometric series where the a value from the geometric series is 1, that's the constant that's in front of the series, and then our r value is going to be x. Technically, it should be the absolute value of x. Remember, we'll just label it as x then. Also remember with geometric series that it converges as long as the absolute value of r is less than 1. Thus, our series converges as long as that absolute value of x is less than 1. Not only do we know that it converges for a geometric series, but we know what it converges to. Recall the geometric series converge to that sum a over 1 minus r. So for us, this particular series is going to converge to 1 over 1 minus, and remember that my r is now x. This is a very powerful thing that we just showed. What we just showed is that 1 over 1 minus x is the same thing as our infinite series, 1 plus x squared plus x cubed plus forever and ever and ever. We're going to use this a lot here in the next couple of sections. The purpose of this is that we're going to take maybe a complicated looking function. So here we have a kind of complicated looking function, and we're just going to change it into an infinite polynomial. When it comes to derivatives and integrals, any kind of theorems that we've seen here in the past 2 or 3 chapters, working with polynomials is a lot easier than working with anything a little bit more complicated here. So if we can change more complicated functions into polynomials, it'll help out with the calculus in the future. Okay. Now, we had to work in this particular direction because we've been working with series so far. But eventually what we want to get to is I don't want to give you the series and ask you what it converges to. I want to give you the complicated function and have you tell me what the power series is that generates that function. So here we're going to change focus. Instead of thinking that that function that we have, 1 over 1 minus x, is the sum of our power series, we want to think that the power series as the partial sum of that function 1 over 1 minus x. So basically what we're going to be doing is we're going to be changing complicated functions into polynomials. All right, so let's look at one a little bit more complicated than this example. And then I'll show you some graphs to really prove that this is working out. So quick example, consider. So now we're going to be considering the infinite series here, 1 minus 1/2 times x minus 2 plus 1/4 times x minus 2 squared. And there's going to be a bunch of these, so just plus. Just to write this a little bit more generically, we're going to have a negative 1/2 to the n out in front, and then an x minus 2 to the n, not capital N, sorry. And then this is going to go on forever and ever, so we have this infinite series. Another way to rewrite this one, just in the notation that we've been using so far, would be like the strength of the infinite series as n goes from 0 to infinity. Of that a sub n term there, the negative 1/2 to the n, x minus 2 to the n. Okay, this is going to be a power series centered at positive 2 with the way that we have it written here. So we have our coefficient, negative 1/2 to the n, and then we have our x minus a to the n out in front here. Okay, this is also a geometric series. So we're going to have our starting value, our a value, that's just going to be whatever the first term is here, which is the positive 1. And then every single time, we're going to be multiplying by a negative 1/2 times x minus 2. So for the geometric series, my a value is just 1. My r value is going to be that negative 1/2 times x minus 2. And you can distribute the negative 1/2 in there if you really want to. So just doing that real quick, we can rewrite this as negative x minus 2 all divided by 2. Okay. Remember that for geometric series, this converges as long as the absolute value of r is less than 1. So for us, this is going to converge as long as the absolute value of negative x minus 2 over 2 is less than 1. This is the same thing. Because of the absolute value, that negative sign just disappears. And then any time you have an absolute value and a less than, this is where you want to squeeze. So we're going to squeeze x minus 2 over 2 in between negative 1 and positive 1. All right, so again, absolute value less than a number, you squeeze it between the negative and the positive. I drop the negative sign on the x minus 2 over 2 because of the absolute value. All right, to solve this, we're going to multiply by 2 on both sides and then add 2. So just to multiply by 2 on both sides, we'll get negative 2 is less than x minus 2 is less than 1, or positive 2, sorry. And then to add the 2 over, we get 0 is less than x is less than 4. This has a name to it, which we're going to get to in the next section. So just know that this is an important interval moving forward. All that matters to us for now is that this is the x values for which this infinite series converges. We have not found out what it converges to yet. All we know is that this only converges as long as my x is in between 0 and 4. To figure out what it converges to, remember this is where we want to do the a divided by 1 minus r. Our a is just 1. And we're going to divide that by 1 minus, we have to be a little bit careful here. Our R value is negative 1/2 times x minus 2. And then just solving this real quick, you play around with it. It shouldn't be too hard to see that this converges to 2 over x. So distribute, the double negatives here cancel out to be a positive 1/2. Distribute the 1/2 into there. You have to do a little bit of magic to cancel this out, but 2 over x should be the final answer there. If you want to, you can write out what we call the polynomials of the power series, and they're written like this. So p sub 0, this is the 0th polynomial. This would just be plugging 0 into my series up here, which would just give me the value 1. The next polynomial would be p sub 1. This would be plugging a 1 into my series up here, which would be getting the first 2 terms. So 1 minus the 1/2 times x minus 2. You want to think of these, remember, as being those partial sums from before. So this p sub 1 is like the partial sum of my series, just the first 2 terms. P sub 2 would be the partial sum of the first 3 terms. So it would be the 1 minus the 1/2 x minus 2, and you'd also have the plus 1/4 x minus 2 squared. And then you can just keep going and you can go and get all these different polynomials. You want to think of the index here as being the degree of the polynomial. P sub 0 is the first degree, P sub 0, this is the 0th degree, P sub 1 the first degree polynomial, P sub 2 the second degree polynomial. This, you want to think of as the partial sum of 2 over x. All right, I went into Desmos here and I graphed this out a little bit. So this is the graph of the function that we know our sum goes to. It goes to this 2 over x function. This is our infinite series. All right. What I've graphed right now is that this is just that first polynomial p sub 0. So of course you just get a 1, so you just get that horizontal line. I'm going to play this, and as I play this, my a is going to keep increasing. So then you're going to see the first degree polynomial, the second, the third, and so on and so forth. And what you should notice is that my partial sums are eventually going to approach my 2 over x. But not everywhere. It is only going to approach it on that interval of convergence, which is in between 0 and 4. So all we care about is this section here between 0 and 4. And I want you to watch as the green line slowly starts becoming the blue line as my indexes increase. So I'm going to hit play. So notice that the higher the index, the better my graph starts to approach, but only between 0 and 4.